So, hello everyone, this is Akshay here, and welcome to our channel of our GFG POTD streak of day 101. So, if you're new to this channel, please like, share, and subscribe so that we can learn, grow, and maintain our streak together. So, let's see what today's question is about. It is about the selecting the nodes. The question name is select nodes is a hard category question, and let me tell you before we start that this question is actually a good question and it will be a little bit tricky to understand. So I just request you to bear with me till the last, because to understand the code which I am about to write is very easy, but the things that how that code is working is a bit tricky to understand. So before I start the question, let me give you a referral of this question. That if you visit this 968 of the lead code question that says binary tree cameras, it's exactly the same question as we have here. Only difference is the the function which we have been given here. It starts with the tree node root, and the function which we got in the POTD streak is different. We got the edges, and that's where the entire problem lies. It's very easy to explain you the question and how it is and how it will work, but it will be a bit tricky, a bit difficult to understand that how the code is working for this POTD. As for this lead code, it's very easy, just 7 to 8 lines of code and you can do it. So what's the question? So the question, we will first read this question and then we will go to that question. So you are given root of the binary tree. We install cameras on the tree nodes. Camera is nothing but each camera at a node can monitor its parent, itself, and its immediate children, right? So in the example one, if you see that if I place a camera at this node, it means that it can track its parent and its children, right? And itself also. So we have to return the minimum number of cameras needed so that all the nodes can be tracked in a tree, right? So for this example, these minimum number of camera requires is 2 here, right? Now let's jump back to the question, right? So given n nodes of a tree and a list of edges, find the minimum number of nodes that can be selected to light up all the edges of the tree. And edges lights up when at least one node at the end of the edge is selected. And this is the tree given here. And selecting nodes 2 and through lights up all the edges. So let me explain your question. And while explaining it, I'll give you the answer also, that how we are able to solve it. It's nothing but a simple tree traversal. It's just that they have given in our question as the 2D edges. That's make this question a bit difficult to code, right? To code, not to understand. Okay. So there are edges given. If I try to draw that's why I have pre drawn all the things here so that we can minimize the video of this uh, s- lecture today. So edges are given from 1 to 2 and 1 to 3. That means there is a node 1 which is giving 2 and 3. Similarly, 2 is pointing to 4. So 2 goes to 4, 3 to 5 and 6, right? So we need to place the cameras so that each and every edges get lighten up, right? So let's start about thinking that let's try placing the cameras from the leaf edges. So if I place the camera from leaf edge, that is 4, 5 and 6, then 4 will cover 2, 5 will cover 3, and 6 will obviously cover 3, because 5 will cannot cover it will cover only 3, not 6. So that's why we have placed the all cameras at leaf nodes. This is just one possibility. So 2 and 3 will be getting covered by 4, 5 and 6, and but one will be still remaining, right? So we need to place a camera at one also. So then we can say that there are four cameras. There is one possibility that we can place four cameras if we start from the leaf node. The second possibility is, let's do not start from the leaf node, right? If we do not start from the leaf node and a level just above it, then the two will be pointing to this four, as well as if could have other children also. In this case, that would have also been lightened up, right? So okay. And for this tree just above the level of leaf node, it will cover the 5 and 6 at the leaf node, and this 2 and 3 will also cover this root node also, right? So I can say that only two cameras are required to cover the same tree again here. So this is the most efficient approach, and that is the only logic to solve this question, right? So we do not have to process the leaf nodes, right? We just have to place the camera at the position which is non-leaf, as well as which is non-leaf, and we have to start from the bottom level, the second bottom level of our tree, right? So what can I say, what can I deduce, that uh, the camera should be placed on such a node where if it is a parent, if it is a parent, and or I can say that if parent is null and node is uncovered. Node is uncovered. Parent is null in the sense I'm talking about the first root node. You can say there is no parent of it, but it there would have been case that if it is not covered, then only would have chosen this as our camera here. But you can see that this the above, the below 2 and 3 will cover this one also, right? So the second case will be that if any of left or right child is not covered, right? As you can see, this 5 and 6 was not covered, so we placed 3, the camera at 3. Similarly, you can see that 4 was not covered, so we placed camera at 2. And as you can see for this one, the root node, the children were covered, right? So that's why we do not place it, because if the children is covered, it will link up to the all the possible edges, from the root, from the node itself and its children. That's the entire logic of this question to solve it. So if you try to solve this question at the lead code, it will be very easy to write the code of it, because they have given mentioned the root node, and you just have to do a traversal. It will be as simple as that you are doing an in order traversal, but the complexity changes in the code thing because they have given the edges. So first we need to make a tree, or let's say we have to make an adjacency list in the case of graph, and then we have to traverse it, right? So that's what I have written this step one here as, to make an adjacency list, and they will make a, and then also after that we'll make a value array which will be pointing, which will have a 2D array which with two entries for each, two a list of two entry at each index. And why it is that, because you or yourself observe that there will be two possibility of selecting a node, to select it or not select it. So the first entry will be implying to the thing that some of the children which is actually having a value 1, having a value 1 means that that the node is selected, right? And the second entry is for the 1 plus the sigma of the minimum of the children which is not selected, or plus the children which is selected, right? So let's just get started, and we will do a dry run of the code, and we will understand that how the things are working, right? And then the third step will be just starting the DFS from 1 comma 1. So I am here pausing the video, and I'm doing the first two steps, that is making adjacency list. That is very normal. So let me do that, and let me pause the video now. And before that, you also try to write the code yourself for this adjacency list and resume the video. So here goes our step 1 and step 2 code, and step 3 as well, where we call the DFS, right? So let me give you a quick walkthrough. That step 1, we just made an ADG array with the entries at the array list, right? So this will look like this, that we have this entry as 1 to 6, and at each entry we have the array list of 2. We have the array list where we store two values, that is the first row will be 0 and the second entry will be 1. Okay, so to define the entries, we use this value. So this was the step 2, right? This adjacency list is looking like this. Like this. Like one was actually was having the branch to 2 to 3, right? So one has 2 to 3. Similarly, 2 will have 1, and the vice versa, right? Because there was no directed edges there. So this is where we have made the adjacency list, and this is the step 2 of making a value array, where I just showed you that the first column is for sum of the children which is visited, and the second one is 1 plus sigma of the sum of children which is not visited, or this sum of children which is visited. So here goes our second part of the value array, and we just call the DFS. And in the DFS, we just have to make sure that we do not, let me write it for you. We do not process the leaf node. That's the main logic here. And then we just have to see that if the left and right node is not visited of a particular node, then place the camera there. That's the just the main logic. So let's write the function. So let's make a function that uh, public void DFS, and since the first thing we need to pass as the adjacency list, so I will say array list of integer, and it has the adj name with the array type, and then I will pass the source, and then I will pass its parent, and then int value, the 2D value array, right? Okay, so how to make sure that we do not process the leaf node? So let me write the code, and then I will explain it to you that how that thing is working and is not processing the leaf node. So for integer, we the ADJ of source, I will call for each and every neighbor, I will call the DFS, right? And for each and every neighbor, so that particular neighbor should not be a leaf node. So here is the case that we do not process the leaf node. And how is that getting managed? By using this statement, that if v is not equals to parent, right, then that means that this particular thing, if it is equal, then that means that it is a leaf node. If it is not equal, then that means that that node is not a leaf node. How is that getting handled? So let me just pass this function and then I will explain you. So v source and then value, right? Okay. Okay, so let me give you a very quick dry run here. I have made this recursion relation just for you guys to make you understand. So what we did, we call the function for f of 1 comma 1, the source and the parent. And then what we did, that the neighbors of 1 were 2 and 3, right? So as you can see, 2 and 3 I have written here, right? And we call this function for 2 and 3 again. So if we call the function of 2, it has passed that 2 has now, if you visualize the tree, it was like this, right? So now the 2 is the source and the parent is 1, which I have taken from here, right? And I have passed it again. So now if we come now, this, since there's a recursion, right, so we have to pass the children of 2, that is 1, that is 1 and 4. That's what I've written, 1 and 4. But now as you can see, the parent itself is 1, right? And as you can see, let me tell you. So the parent itself is 1, so we did not process it. Now it was like 2 to 4, right? And this was the leaf node. So let's go. So from 2, the other children was 4, right? And as you can see, if we call function 4, then it will be function of 4 comma 2 comma val. Function 4 is nothing, it is v, and 2 is the source. It is coming from the upper function parameters, right? And then what is happening, that this function is calling that 4 has the linkage with 2, right? Has the linkage with 2. And as you can see, the parent of the children of 2 has the parent as 2 from from this parameters we pass in the recursion. So that means that you do not have to process it, and you can see that the processing stops here. And we again, the callback comes to it's just uh, the previous function that was in recursive call stack, and then we process it, right? So that's make sure that you do not hit the leaf node. Okay, so let's get back to the coding section again. So that is making sure that you not hit the leaf node. So if that's not the leaf node, then you need to do, then you need to process it, right? So what I am doing integer b, the same thing that I have written here, that adj of src, right? Then I will again mention this condition that it should not be a leaf node. And I am updating some values now, that src of 0 is plus equals to value of v and 1. What it is doing is it is updating, it is actually doing camera plus plus, that this is the node we need to maintain, we need to increment the camera count to get the answer. Similarly, for the value source 01, which we discussed in the starting, that it will be updated to the plus equals to math.min math.min value of v1 comma value of v0. Okay, so it may be very difficult to understand what is these lines doing. So let me give you a very clear clarity as well as the dry run for this code. This is nothing that we are doing camera plus plus, where we are seeing that it is needed to, that camera should be placed there, right? And this second line is what it is doing is it is actually maintaining the minimum value, the minimum value that is required, that if we take the children from the from the same branch, and if we do not take the children from the same branch. So let me give you a very quick dry run of the entire code here, right? I have made this dry run just for you. So take out your pen and paper quickly and just write it down with me, so that you can do the dry run cases, dry run for the next test case, and you can understand more properly. Okay, so this was 1 comma 1, right? And for each and every uh, source we were iterating, and we were calling this thing, we are calling the DFS. And after the DFS get over, we actually process those integers, we actually process those neighbors. So let us get back to the paint again. So for this thing, as you can see, for one the neighbor was 2 1 2 and 3, so we passed 2 here, and we process it and we found that from 2, the from 2 I went to 4, and this was the leaf node. So yeah, so I went back. So that's what happened, I went back, it did not process it. So I went back to 2 again, right? And I process it. So I am now making an edge from 2 to 4. This is what happening here. I am not making an edge from 2 to 4. So I need to update that at 2, 4 was not visited. So I need to push a camera here at node 2, and that's what I have made this value 0 to 1, right? And this second value from 1 to the minimum of these two value, to the minimum of these two value plus the increment 1, right? The value which is there at plus the minimum of these two values, right? Okay, so there goes our this thing 2 to 4, and then we recur back to this 1 to 1, the parent call, right? So the processing for 2 is done, and now we have to process the left part, that is 3. For 3 we see that the neighbors were 1 5 and 6, right? So 1 we cannot process it because it's like the parent is still pointing to its neighbor, right? So we cannot process it. That's what the thing came in touch, that if v v is not equals to parent, so it is handling as well as the, it is handling the leaf node as well as parent, it is handling both the things, right? Okay. so so 1 is not processed and the 5 is processed again for 5, and source is passed. Source is always passed here, as if you look at the code, source is passed at the parent in the new recursion, and then it sees that 5 has again the neighbor of 3, and the 3 and 3 collide, so we do not have to process it. Similarly for the next for loop, after the recursion and there is a for loop, right? So the neighbor of 5 was 3 and the parent is also is 3, so that for loop will also not run. Similarly for the case of 6, that 6 has the neighbor 3, and 3 itself is the what, 6 has the what, the linkage with 3, and the 6 has the parent as 3, right? So and you are processing 3 again, so that should not be the case, right? So that's what there was this thing, that v is not equals to parent. So here goes, we cannot move forward in this case, as well as the for loop will also stop due to the same reason. At the last step, where 3 was actually, we have to process all the neighbors of 3, right? So the neighbors of, where we have the second stage of for loop, this is nothing but this for loop at line number 64, right? And this is what we are doing in the try run. So the neighbors were 1 5 and 6, and as you can see the parent was 1, so we should not be equals to p. So that's why this first case was debarred, we do not have to process it. And for 5 1 we are processing, for 6 7 we are processing. This is nothing that we are, this is actually what we are doing is that we are making the edges from the source to v, that is we are making from 3 to 5, that's what I've written, 3 to 5 and 3 to 6. And because we are doing so, we need to place a camera there, right? So for 3, if I'm visiting 5, and from 3 if I'm visiting 6, and 5 and 6 both were unvisited, so I need to place a camera at 3, right? So that's what I have done, that 3, this index is actually belonging to 2, right? And why? It was nothing but the sum of children visited, right? So it visited 2 children, 5 and 6, that was, it is saying that the first entry 2 is saying that I have visited 2 children, that's why my value is 2, right? Right. And the second entry is nothing but the minimum of the children visited or the children not visited plus 1. So that's what the second entry is about. So this is all the code steps that is following. And for the third, for just the parent call, now it's left to execute for function 1 and 1. So 1 and 1, the neighbors were 2 and 3, right? And parent is 1 and 1, and the source is 1 and 1 also, the same. So what are we doing? We are doing nothing but making the edges from 1 and 1 to 2, from 1 to 3, right? So since we are making the, we are visiting 2 and 3 from 1, that's what it is pointing to 2 here. The first entry is pointing to 2, and this is handled using this line of code, that is saying that I am nothing but pointing to 2 and 3. So I am visiting the two children which is having, So I'm visiting the two children, that is visited. So we have this 2 here, and the second entry has the same thing as I said, the sigma of 1 plus the minimum of child visited, and the or is compared to child not visited, right? So this is the case, this is the not visited and this is the visited, and we are doing 1 plus in the minimum. So how is this thing handled? So if I'm making from 1 to 2 and 1 to 3, so I'm always picking this thing. If I'm always picking this thing, so what is the minimum? 1 comma 1, that is 1, right? So I have mentioned 1 plus 1. What's the minimum of 2 comma 1? If I'm making 1 2 3, it's 1, so I have again plus 1, so that becomes 1 plus 1 plus 3. And at last we just have to, since we are at root node now, all the things are processed. So if we talk about the direction of travels, we are processing left first, then we are processing right first, and then we are at this root node. So that means at the root node we are getting our answer. And as you can see, if you do, this is the first entry is saying 2, right? This is saying 2 and this is 3. So that means that you have made two two you have visited two children, that is which has the value as 1, and this thing has the minimum of this thing. So at last we have to return the minimum of these two, and then only then you can hit your answer, right? Why I'm saying minimum of these two? If you consider the case that it is 1 2 and 3, then if you do not apply this condition, then the value will be returned wrong. Try to dry run it for some more test cases to get a clear understanding. So I was saying that from the starting that the code will be a bit complex to understand, maybe for some users, but at the last it will be worth it. Just try to dry run the code or dry run the logic for some more test case, and you will good to go. So that's it. uh, Everything cannot be like served in a plate for you for this complex questions. You just have to think in a direction, okay, that's possible. If you just move in this direction and try to dry run it for more test cases, specifically in case of recursion, specifically where recursion happens under the for loop, right? So many of you will many of good educators on YouTube will not tell you that. They will just tell you the good examples, and then will not touch this examples. Okay, so that's not the case. So till then, if you last thing, that's my DSR repository. You can start and fork to get help with the source code, and that's my Instagram channel. You can get in touch with me 24 into 7 for any doubts and guidance if you may have, and you can always ask the doubts about regarding this question also in the comment section, so that I can also see that how many of you are getting doubts and how many of you are able to understand the question. Till then, bye bye, take care, and keep running, keep growing. Bye.